we are going to talk about Stirling's approximation and the related limits theorems, which will help us to make sure that we understand everything that is going on in this limit section. Okay, so today in this lesson, we'll try to make sure we understand Stirling's approximation first, and then we'll look at some of the related theorems of limits, such as Stolz-Cesaro, then Cauchy's theorems, the first and the second, both of them. So like we'll be trying to cover all these three in this lesson, and possibly with a bit of examples to enlighten our views on this topic. Okay, so let's begin. So what basically is Stirling's approximation? I will just give you a good guide over this, and I'll try to derive it from the basic and scratches so that we get to know these things from the very elementary methods from which they were built. Well, this is a method which essentially says how to approximate n factorial, isn't it? So this is basically a method which will tell us how to approximate n factorial, and would like to derive it on some grounds on the basis of some of the integral theorems which we have learned using Cauchy's and Riemann's theorems. So the basic fundamental formula that comes from this is n factorial is almost equal to root over of 2 pi n of n by e to the power n. So this is the formula for n factorial. Well, we might check a few of the values, like you may directly consider that root over 2 pi n e are very close to each other. They're very close, and that's why 1 factorial is 1, which is very close to each other. So it's obviously not working, but this value gets closer and closer as n tends to infinity. So it's like this, that limit n tends to infinity, n factorial divided by root over of 2 pi n times divided by n by e to the power n is equal 1. That is, the limiting value of both of this is same, and the limiting value of n factorial approaches this. So we'd like to prove this theorem also, like, because we cannot just take any formula for granted, and right now it's not really in our tasks to prove this, but we'd like to have a proof for it so that we can understand how does it actually come, because the proof is not really very much elementary in terms of mathematics. Like, we have to use something we call as Riemann's integral, not really the Newtonian integral we are used to. In class 11 and 12, what we learn is Newtonian integral and not Riemann's integral. Riemann's integral is quite different from it. So Riemann integration is a whole new topic. So let us try and derive this. Stirling's approximation. Well, this comes from a lot of ways, but the first one we'll try to do is by Riemann integral. Okay, now what to do with this formula? Well, this can be derived roughly by noting a sum equality. We all know that the sum of logarithms can be turned into products, right? So ln of n factorial is basically j equals to 1 to n ln of j, right? This means it is equals to ln of 1 plus ln of 2 and all the way up to ln of n. So This is basically because the product sum turns it into a product, and that's why it happens. Now this sum basically can be approximated by an integral. How do we do that? See, basically it can be done like this. What we do is that we approximate a sum like this. Ln of j. This sum is approximately equal to the integral of 1 to n ln x dx. Now this is easy. This can be approximated like this from n to 1, which gives you n ln n minus n plus 1. So this is one kind of approximation we can do for any kind of sum, because the sums are discrete, because the sum takes on values from 1 to n only at integer points, but the integration takes on values from all the points, right? So basically the integration is always greater than the sum, but in nearwise it can be approximated like that, because the logarithm value becomes 1. But by this approximation can also be approximated using Euler-Maclaurin formula. The Euler-Maclaurin formula says that, and using the combined trapezoid rule, this is going to be a bit more nasty than it should be, but still I'm going to do this. Euler-Maclaurin formula generally gives you that ln of n factorial minus half of the first term plus the second term of this, that is ln of 1 plus ln of n, will be equal to ln of 1 divided by 2 plus ln of 2 plus ln of 3 plus all the way up to ln of n and this gives us at the end half of ln n, because we want the logarithm's first values and the third values to be kept. So basically the first and last terms are halves, right? That's what we call as the trapezoidal rule. Great. So we put a half here, we put a half here, correct. So that's what we call as the trapezoidal rule. Now, in addition to all of this, there is something else. There's something else what we call by approximating is this. So we write the equality and Euler-Maclaurin formula in its complete terms like this. The left hand side is basically ln of n factorial minus half of ln n, and the right hand side. Now, the integral that we found, this minus this plus 1 plus, there's a sum involving Bernoulli numbers which appears everywhere in it. Cannot really deny them. This is the Bernoulli numbers. The Bernoulli numbers appears the expansion of the Riemann zeta functions, and they are quite wonderful wonders, to be fair enough. And there is a remainder of R of mn. Now this is the ultimate form of the logarithm. Now from this you can easily define, if I were to erase this, I could easily write you the answer. From this you can easily derive the answer, which is, after some more manipulations which are really out of this course, I don't really suggest using this, but still you can derive root over 2 pi n n by a to the power. There are other derivations of the same thing which you can define. They come like this. Let's do another derivation and let's see what we can do with that. I've already talked about the gamma function, and if not, you haven't heard of it, we'll be going to hear it in our next few lessons, where we'll be talking about only the higher integrations of gamma functions. Okay. So basically, first thing is that the gamma function is n factorial is defined as 0 to infinity e to the power minus x, x to the power n dx. Correct. This is the gamma function. Now if you do some changes to it, it will give you e to the power minus x, and x to the power n can be written as e to the power n of ln x, right, dx. This gives you 0 to infinity e to the power n ln x minus x dx. This is an alternative form which we have brought it into, right. Now from this point we'd like to introduce the substitution of x equals to ny. So this will give us dx is equal to n of dy, isn't it? That will give you 0 to infinity e to the power n ln of ny minus ny dy. 0 to infinity e to the power n ln n into e to the power ny ln n into e to the power like ln of n in one side and e to the power n into ln of y on one side, and this gives you into e to the power minus ny dy. And obviously there will be not dy, there will be an n dy here because dx is dy. Right. Okay. So this really breaks up into e to the power n ln of n into n 0 to infinity e to the power n into ln y minus y dy. Correct. But this sum can be approximated, this integral can be approximated by Laplace's method, which gives this equal or not really equal, approximate 2 pi by n e to the power minus n, and that gives you your answer. That gives you your answer as n factorial is approximately equal to root over of 2 pi n by e to the power n. And there you go, you have your answer. This answer will give you everything you want, and that's how we prove this formula for Stirling's. Correct. Okay. So this is Stirling's formula. I'll show one example for it and try to approximate the binomial coefficient, and that will be it, because you can use it in any formula you want. And then we'll look forward to Cauchy's, not necessarily in this video, but we'll look forward to Cauchy's and Stolz-Cesaro's also. Okay, let's see if we can try and approximate the 2nCn. So what is this basically? This is 2n factorial divided by n factorial squared. Correct. So let's go one by one. 2n factorial. So this 2n factorial is basically root over 2 pi of 2n, isn't it, divided by 2n by e to the power 2n. Well, and the n factorial squared will be equal to 2 pi n by e to the power 2n, isn't it? So the difference, that is their quotient basically, will be equal to root over 2 pi into 2n divided by 2 pi n into, and because both of them share the same power, we have 2n by e into e by n to the power 2n, 1 by root over 2 pi into root 2 by root n, and n gets cancelled, e gets cancelled, it's 4 to the power n. Root 2 and root 2 also gets cancelled, and this equals 4 to the power n by root over of 5. So we have a good approximation right now. So this gives you the good approximation that 2nCn is equals to approximately 4 to the power n by root over pi. And this also gives you a good approximation for pi, that pi can be approximated as rewrite in this way: pi can be approximated as 16 to the power n by n 2n cn to the power minus 2. So this thing, so basically you have directly a problem of a limit, that limit n tends to infinity, 16 to the power n by n 2n cn to the power minus 2 is actually equal to pi. This is one of the most important results, and this kind of results you can get at ease by using this theorem of Stirling's. Okay, so that's it for Stirling's. Let's go on to the next theorem, Stolz-Cesaro's. So the Stolz-Cesaro Theorem says if an plus 1 minus an divided by bn plus 1 minus bn equals L, then this, whatever we are looking here at, the Stolz-Cesaro theorem, the difference of the two sequences, the difference, basically the common difference between the two sequences, between the n plus 1th term and the nth term, divided by another sequence bn. So basically you have two sequences, an and bn, and this equals to L, which is finite. In addition to that, Bn must be unbounded. Bn must be unbounded and monotonic. Unbounded and monotonic. Then limit of an, basically this is also a limit, by Bn also equals to the same thing and is equal to L. This is basically how it comes, but you can really prove it easily with some trying tricks on theorems that are illustrated in the general limit theorems by Cauchy basically. So these theorems are like this, that let's do one of those theorems. Let's say we want to find limit 1 plus half plus 1 by 3 plus 1 by n like this, and which is basically the harmonic numbers divided by, let's say, n. We want to see if this limit exists or not. We're not really sure about it. We want to see if this exists or not. So if we have to first understand that if this thing can be evaluated by the Stolz-Cesaro theorem or not. Right? So this thing, this is basically an plus 1 minus an, right? So what could be an plus 1 minus an? So if you can express this as an plus 1 minus an equals to hn, then you are done. Because then an plus 1 will be hn, which is the harmonic number, plus an, isn't it? Also, this theorem can be done by a couple of other theorems like the squeeze theorem and the others to establish a bound between this, isn't it? One of them is that hn is sometimes equal to log n minus n, sometimes. So using that we can prove that this is basically going to be a negative number, which is not really true. So this bound doesn't work here. So what about the Stolz-Cesaro theorem? Because an plus 1 is hn plus an will be hn minus 1 plus an minus 1. And this will basically go up to h1 plus h2 plus hn, isn't it? So this is basically our an will go up to hn minus 1. So summation up to hn minus 1. These are a. What is bn? Bn plus 1 will be bn plus n, or n plus n minus 1 is bn minus 1. So basically it's going up to b1, which is basically n into n plus 1 by 2. So this is also our bn plus 1 minus bn, which will give us the answer. So bn is basically n into n minus 1 by 2. Now bn is monotonically increasing, that's correct, and it is also unbounded, isn't it? So this thing can be represented like this. If this is equal to some finite number, if that is given, if let's say this thing was given that an plus 1 minus an by bn plus 1 minus bn is given, then this thing will be equal to the same number, that is an, that is hn sum up to hn minus 1 divided by n into n minus 1 by 2. This thing will be exactly equal to this thing. So that's the entire essentiality of the theorem. First, from the theorem we derive out the terms, that if this is equals to an plus 1 minus an, then what will be our an, what will be our bn, and then you just find out the limit. One of them will be definitely given, and if you can find one of the others, and then you will definitely get the answer, because they are correlated with the same variance theorems. So that's basically the Stolz-Cesaro theorem. There are not much applications of it, but it is worthwhile to get it known. Okay, last but not the least, there is a Cauchy's theorem on limits, which says there are two Cauchy's theorems. We will discuss one by one. So if there is a good note of theorems on Cauchy's, which is basically kind of an Stolz-Cesaro theorem. So let's say if limit n tends to infinity a is equals to 1. If this happens, then limit n tends to infinity a1 plus a2 plus an n equals to n. So this is how the theorem goes. So this basically gives you the theorem to worry about, that if the term of a series goes to L, so if a sequence actually converges to some number L, then a new sequence which is defined by the average of the terms of the previous sequence also goes to the same number. So this is basically only for knowing. You can apply it directly. No need for a proof. So I'm just going to state this theorem. So you can just apply it directly. Okay. second theorem says that it's related a bit to like exponentials. This says that if limit an plus 1 by an equals L, then limit an to the power 1 by n equals L. A good way to answer this is if limit, let's say n plus 1 by n actually equals 1, isn't it? So this says our an is 1, right? An is n here, so that's why n plus 1 is n plus 1. So it says that limit n to the power 1 by n is actually equal to 1. That's how easy it is to apply. So you can apply this kind of theorem almost everywhere. Also, the previous one, if an is equals to 1 by n, let's say. So obviously limit n tends to infinity, n goes to 0. So then its average 1 plus half plus 1 by n also goes to 0, isn't it? So this was the problem we were talking about, which can be dealt not with Stolz-Cesaro but with Cauchy's theorem. So that's why you need to be careful that which theorem you need to use in order to get success. So that is it for limits. There is nothing more to learn in limits right now. So do your problems carefully, and I do not have much problems and examples to share because all of them I've shared before. Can be done in this kind of ways only. There are not much problems in limits that will bother you. That's it. So thank you.